Okay, everyone, we will start soon. In order to get a smooth pre-conference tutorial session, today we will mute all of the participants, so we will not have noise from the other participant instead of the presenter. So good day, everyone. Thank you for joining us today. Welcome to the fourth tutorial of Asia Pacific Synthetic Aperture Radar tutorial sessions. And my name is Sanjiwana Arjasa Kusuma from the Faculty of Geography, Department of Geographic Information Science, Universitas Gadjah Mada. So this tutorial is part of the pre-conference events of the Asia Pacific Synthetic Aperture Radar 2021, which will be held on the 1st to 5th November 2021. So make sure to check the important dates on the website of APSAR in the apsar2021.org. APSAR was organized by Chiba University, also National Institute of Aeronautics and Space, or LAPAN, and Agency for Assessment and Application of Technology, or BPPT, and also Indonesian Society for Remote Sensing, or MAPIN, and also IEEE GRSS, including the supports from the academic institutions such as the Institute Technology of Bandung and Universitas Gadjah Mada, or UGM. And for today's tutorial, the event is hosted by the Department of Geographic Information Science, Faculty of Geography, Universitas Gadjah Mada. For today's session, we will have 3 distinguished speakers, which are expertise, and each speaker will be given 50 minutes talks and followed by the 10 minutes Q&A sessions. In addition to that, the e-certificates will be given and will be provided through the link that will be distributed sometimes during the tutorial. So make sure that you follow the talk so that you can get the link in order to get the e-certificates. The rundown for this session, the first, before we start the talks, there will be an opening from the chairman of the General Chair of the APSAR 2021, which is the Prof. Josaphat Tetuko Sri Sumantio. To Professor Josaphat, the time is yours.
You can hear my voice?
Yes, Professor.
Okay, yeah. Thank you very much to the moderator and also the all of the participants. And first is I want to thanks to the UGM team, yes, especially to Dr. Kamal, who arranged the today fourth tutorial of the Aperture. Yeah, Aperture is the we will have in Bali next November 1st to 5th, yeah. And like you know that Aperture is the Asia Pacific Conference on Synthetic Aperture Radar. This symposium is co-sponsored by the IEEE Geoscience and Remote Sensing Society, or GRSS. Yeah, and yes, actually 2 days ago we got the official approval from the IEEE GRSS, and like I think you already know that the paper that presented in this symposium will be published in IEEE Explorer, and it is included in the Scopus, and I think it's Indonesian, especially in the scientists need this indexing. Yeah, okay. And I'm as the general chair, and I want to show that the call for paper. Yes, like you know, next April 30 is in the deadline for the abstract. Yes, and then for the paper submission is May 31st. Yes, I hope first is please submit the abstract is in the next April 30, and I encourage the young scientists especially, and then also the student can join in this symposium. Yeah, and the symposium is actually we also consider for the participant from Asia, Southeast Asia especially. Yes, and who doing the research in general remote sensing. We also serve some session, yes, that including the optic and new remote sensing sensor, and also the application of the remote sensing. Please join us, yes. And okay, notification of the paper is August 1st, and deadline of the early registration August 31st. And we consider the registration fee is, I think, is with the low cost, yes, especially for the virtual presentation. Please also encourage your student, yes, and your researcher to join in this symposium. Yeah, and for the preparing of this symposium, we also holding the tutorial. It is the pre-conference of the Aperture 2021. Yeah, and today is the fourth, yes, of the tutorial, and when the Dr. Agustan and Dr. Meta, and also Dr. Marwan, yes, from the DLR, yes, and will present the remote sensing, and especially in the synthetic aperture radar. Yeah. Okay. For the detail is please check in this website. And then you can find the template how to submit the paper. And please help us to spreading this information to your colleagues. Yes. Okay. And thank you very much. And I hope all of you can enjoy and to learn in this tutorial. Okay. Thank you very much. And I give the time to the moderator. Yeah. Thank you.
Thank you very much, Prof. Josaphat. So for those of you that are interested in joining the conference, please make sure to check the website of apisar.org and also check the important dates in order to submit your research. So as I mentioned before, we have three distinguished speakers. The first speakers will be Dr. Agustan. Dr. Agustan is a chief of the Indonesian Society for Remote Sensing, and he is also working in the BPPT as a research associate at the Center of Technology for Natural Resources Inventory, or PT ISDA. Dr. Agustan graduated from the Geodetic Engineering in 1997 and studied Master of Spatial Sciences in Kartini University from 2000 to 2003, and graduated doctorate from Nagoya University in the field of Earth Sciences in 2010. For Dr. Agustan, you have 45 minutes to present in this session. Thank you.
Thank you very much, Mr. Moderator. If not, I'm mistaken, you're Dr. Sanjiwana, yeah?
Yes.
And also graduated from Nagoya University.
Yeah, so
we are same alumni.
Yes.
Okay, thank you very much. Good afternoon, ladies and gentlemen. It's very happy to see you again in the fourth part of the Aperture tutorial. So this is like a pre-event for the Aperture 2021. So I'm very happy to have a session here to share about what is the remote sensing technology for disaster monitoring, as mentioned before. So at the first time, let me greet some distinguished speaker and distinguished fellow here, Professor Josaphat, Dr. Wahyudi Hasbi, and Professor Ilham Alimuddin, Pak M. Kamal, and others. That the name is listed in the my screen, so I'm sorry, I cannot mention one by one. So for this afternoon, I'm very happy to prepare and to share what I've learned and what is the experience related to the remote sensing and then disaster monitoring. So let me share my presentation. So clear, yeah? You can see all the screen?
Yes, we can.
Okay, thank you very much. So the topic that I've asked to talk this afternoon related to the remote sensing technology for the disaster monitoring. But our main goal is to attend or to write a paper in the Aperture 2021. So mainly maybe in the next part of my presentation is related to the application. So maybe in the first session, we would like to discuss about the general issue related to the remote sensing and disaster. So as we can see, this is my introduction. At the first, we would like to understand what is a disaster. So from the UNDRR, the disaster is defined as a serious disruption of the functioning of a community or a society at any scale due to the hazardous events interacting with conditions of exposure, vulnerability, and capacity leading to one or more of the following: human, material, economic, and environmental losses and impacts. So this is kindly that there is a hazard, yeah, and we can distinguish because so many definition of the disasters, and also the classification of disaster itself is various. For example, natural disaster, man-made disaster, and other things. But we can notice that if we talk about the disaster, so it should be related to the human people, because if the hazard is occurred in the area without humans, so maybe we cannot say that it is a disaster. So in the second point that I would like to share is, I would like to say that hazards are predictable or inevitable, but disaster are not, because disaster is occurred. Yeah, so we cannot sometimes we cannot avoid them. And then the third part, the third points is risk from hazards can be estimated. So that's why we would like to improve our knowledge, our science, and our technology, how to estimate and how to predict the hazard and the impact. So this is the role of the science, including the remote sensing. So basically, as we throw back again, the basic definition of the remote sensing is how to recognize and distinguish objects or phenomena. So we think that remote sensing can be used in regarding to detect or monitor, or to predict, or to see the impact of the disaster. So because disaster we can classify into some phenomena. For example, in this icon here in the left part of the screen, we can see a lot of disaster, like related to the volcano and hydrometeorological disaster, for example, and hurricane, and then like tsunami, earthquake, and also related maybe technology, failure of the technology, for example, is also we can classify into disaster. And also maybe related to the food scarcity, maybe it's also related to the disaster. So many things of the disaster can happen. Then that's why we need the approach of the geoscience and technology to improve our prediction, and also to avoid the risk, or to minimize the risk and the damage of the cost related to the disaster. So we can understand that one of the technology is remote sensing. And remote sensing can observe all the phenomena of the disaster phases, because we can understand that disaster, especially for natural disaster, has a cycle, or it has a phase. For example, before and after. So we can, as a refreshment of the remote sensing system, at least we have three components, the three important components. For example, the object itself, and then the electromagnetic wave, and then the sensor and platform. So these components that can be classified, we can understand many remote sensing techniques. For example, for the sensor itself, we can understand that to process the multispectral data, and for the active sensors, we can understand that a lot of algorithm to generate, to process the microwave or radar data. And also for the platform, we can understand that right now the remote sensing various area that can be observed related to the height of the platform. For example, the drone, airplanes or other aircrafts, space platform, for example, international space station, and the most popular one is based on the satellite. So we can understand that this kind of components develop the remote sensing system. And then what is the observed? The observed one is the object or the phenomena. So natural disaster is related to the one of the phenomena can be observed of the remote sensing. So if we talk about the disaster and the remote sensing, so maybe we can understand the cycle of the disaster itself. At least there are 4 stages of the what we call the disaster. When the crisis is occurred or the disaster is happened, so we must make a response to save lives and minimize and immediate the impacts. After the response, the next things that we should do is a recovery, and then after that it can be more to the prevention, and to the next step is the preparedness. So this is the cycle of the disaster itself that we can understand that we at least there are 2 main classification: pre-disaster and post-disaster. And this is cycles. I noticed it's well written by Kosanet et al. In the 2020 that they said that a promising way for what to maximize the impact of Earth observations include multi-risk approaches, which mutualize the collection of time-evolving vulnerability and exposure data across the different hazards. So we understand, based on this paper, actually, we can understand that remote sensing can observe or provide or acquire the data related what things that we should prepare. For example, to make a good map, for example, the potential hazard, potential natural disaster that can be occurred. For example, the potential tsunami, it can be observed from the remote sensing data. And for the response, during the response, maybe we can utilize the drone technology to map the damage area related to the disaster and to make some shelter point to save the lives and other things. So this is very important to understand the cycle of the disaster, and then which kind of technique or which kind of the remote sensing data that you can answer the necessities or each phase of the disaster after the pre-disaster and the post-disaster. So this is the linkage that can we understand by the paper written by Kosanet et al. In 2020. So talking about the remote sensing, especially for the satellite-based remote sensing, why? Because the satellite-based remote sensing have the advantages, especially for the coverage area. Because the orbital height of the satellite-based remote sensing is above the 500 kilometers mean sea level, so the coverage of the area is a huge area in the regional area. At least maybe usually more than 50 kilometers, 50 kilometers. So the advantage of the satellite-based remote sensing is can inform us the condition of the specific area in the near real time. So in the good spatial resolution also. Right now, for the optical satellite, we can understand that at least 30 centimeter spatial resolution is available in the market. So if we can understand the left part of this image, we can see at least there are 3 classification of the optical satellite. The low resolution from 10 to 100 meters for 1 pixel, and then the medium resolution from 1 to 10 meters, and then for the high resolution, less than 1 meter spatial resolution. We can see right now the trend of the optical satellite is 10 to the high resolution, less than 1 meter pixel. We can see here the LO3, Iconos, QuickBird, GeoEye, WorldView 1, WorldView 2, WorldView 3, WorldView 4, ComSat from Korea, Pleiades, and other things. Is all available, the data right now in the market. So we can utilize this kind of data to monitor to answer the cycle of the natural disaster, post-disaster, and before the disaster. In the right-hand side of the image here, we can see the classification of the active sensor or SAR satellites. At least we can understand that there are 3 bands that are available in the market right now. L-band SAR, which is the wavelength around 20 centimeters. That right now is available from ELOS, SICOM, NISAR, and Tandem. And then we can understand that NISAR is a brand new satellite, maybe that the data is very rare. We can found in the market, but for the ALOS is already in the market, which is provided by the JAXA, launched by JAXA from Japan. And then the second one is the C-band SAR. The wavelength is around 5 centimeters. Mainly satellite produced by the European Space Agency or the European country is favorable in this band, in the C-band SAR. Series from AIRS-1, from Sentinel, and RadarSat. And then the most short wavelength is X-band SAR, is around the 3 centimeters. Usually from Italian and Germany, from Cosmos SkyMet and TerraSAR and Tandem X, and Comsat also from Korea is work with the X-band SAR. Why we have 3 different types and sensors and data itself? Because in remote sensing, there is one tools that can answer all the necessities, our necessities. We should combine all the data that can answer our necessities. So we should combine all the things from optical and the SAR to answer, to solve our problem, especially related to the natural or disaster monitoring. So this image I adopt from the paper that written by Elliot in the 2020. So friends here that attend this meeting can read this kind of paper, and it is open access. Yeah, so we can understand what the basically tools that can observe the earthquake hazard, especially based on the remote sensing. So the next part, I would like to talk about the technology push and market pull related to the remote sensing and natural disaster. Right now, very favor and very often we heard that at least there are 4 components that technologies driving the disaster mitigation industry. The first one is the big data analysis, and then the second one is the cloud computing, and then the third one is about the automation and robotics, and the last one is the Internet of Things or IoT. So related to the remote sensing, at least there are 2 aspects that involve to mitigate the disaster. The first one is a big data analysis, and then the second one is cloud computing to make a calculation is faster. Related to because if we talk about the remote sensing data, so we talk about the huge size of image. Because, for example, the optical data or the SAR data, the size of image become one constraint to process the data if we use the common or usual desktop specification. So at least right now we have we have an alternative to process the data based on this kind of offer of technology. For example, if we talk about the big data, artificial intelligence, and cloud computing, so right now we can oftenly see the offer from some data provider or service provider that can provide the information in the short time. Yeah, if we can, for example, by implementing machine learning application for land use, land cover classification. For example, this is from Earth Observation Factory, one of the startup that can provide the services from data available in the anywhere. So they process the data automatically and provide the information land cover changes. then it is automatically detect, and it is work by machine. So we don't make some classification manually anymore. So this is the promising technology that can provide the information more fast compared to manual or conventional data processing strategy. So this is that must be, we must anticipate the development of the big data, artificial intelligence, and cloud computing related to the image processing or remote sensing image processing. And also, for example, many scripting or many algorithm that provide freely in the website. For example, if we explore the Sentinel Hub, we can see a lot of script that written or the many scientists in everywhere, and they provide it is free. For example, the algorithm to detect the forest fire algorithm, and then so now it is depends on us, depends on how people by improve or utilize all the resources available in the internet to make creative things to value edit business, yeah, to edit value of the information that available in the web or the internet. So this is also that we must anticipate for the next stage of the remote sensing ecology. And now I would like to talk or share the experience on remote sensing related and disaster. Yeah. If we understand maybe before tutorial Aperture in the first and second and the third tutorial, we already understand that if we talk about the SAR data, so now we imagine that SAR data is a single look complex images that consist of the two components. The first one is the amplitude or the backscatter image, and the second one is a phase. Both of this component of the SAR data we can utilize for the disaster application. For example, for the backscatter image, if we process, maybe we can solve or answer the problem in the LULCC or land use land cover changes that may be related to the fire disaster or flood disaster. So we can understand which the location that can affected by the forest fire or the flood by applying the land use land cover changes algorithm by processing the backscatter image. Or the second one, we can have the object changes. For example, for the lava flows, landslide, morphological changes, we can understand by utilizing or by processing the backscatter image of the SAR data. So the next component of the SAR data is the phase. So if we process the phase based on the interferometric technique, or popularly we can say that INSAR, so we can understand the ground deformation that occurred in the earth. So from the ground deformation, at least we have a three information there. The first one is a line of sight displacement, and the second one is the horizontal displacement, and the third one is the vertical displacement. From the vertical displacement, for example, we can understand or we can detect the land subsidence or uplift. For the horizontal displacement, maybe we can understand the ground deformation related to the earthquake, for example, or the related to the lava volcanic eruption, and so on. So this kind of the information of the component of the SAR data, we can utilize for many applications of a disaster, including before the disaster or after the disaster, prepare and the post-processing. So it can be utilized to answer the cycle of the disaster phase that already studied by Consonanta in the 2020. This is this slide illustrate the utilization of the SAR data for the backscatter component or backscatter image. This is the illustration by processing with the Snap software, which is the freely available. Yeah. So by utilizing the color composite RGB, very simple one technique, by acquired three epoch, for example, we would like to detect what kind of the burn scar area during the forest fire in the Kalimantan in the 2019, for example. So we have a data before the event, and then at least we have a 2 after the event. So we put in the first data in the red band and the green and the blue. So we can see area that have a different color. So for example, this one and this point and this one. So it is maybe related to the burn scar area, maybe related to the fire. So if we overlay with the fire spot data from FIRS, for example, so we can understand the fire spot, it's a quietly matched with the data observed by the color composite of the SAR image or backscatter image from SAR data. So this is the illustration, one application of the SAR image for the land use land cover changes technique. So the second one, this slide illustrates the backscatter image of the related to the lava flows, for example. So this is the image of the Sinabung volcano in the North Sumatra. So we process the data from Sentinel-1, Siben SAR, and by just very simple visualization by using dual polarization data from the backscatter image, VV and VH, vertical and vertical horizontal polarization, we can see the lava flows related to the eruption maybe of the Sinabung volcano. So this image is acquired on the January 6 and the 2019. So this is the illustration. The remote sensing can easily identify the area that affected related to the Sinabung activity on the January 2019. And also from the backscatter image, we can easily understand the morphological changes. So this series of the image of the Anak Krakatau volcano illustrate how the volcano changes from time to time. Because for your example, for your information, the Sentinel-1 have a 12 days temporal resolution, but we understand that Sentinel-1 have a 2 satellite in constellation, which call Sentinel-1A and Sentinel-1B. Sentinel-1A have a 12 days temporal resolution, same as with the Sentinel-B. But because the sensor itself is identical, so we can process both of the data. And fortunately, the different time of the Sentinel-1A and Sentinel-1B is only 6 days. So every 6 days, it is possible to have the data from whether Sentinel-A or Sentinel-1B. So it is very good and very challenging to us to improve our creativity to process all the data that are available freely. So this data is available freely available, and the software also can be downloaded freely. For example, we process the data here based on the Snap, that also we can obtain it without any license. Yeah, so we can understand the morphological changes of the Anak Krakatau volcano since 16 December 2018, before the big eruption. So we called it in the stable phase. And then during the eruption, starting from the December 23rd up until January 24th in the 2019. So we can see the evolution of the differences of the morphology of the Krakatau from destructive and then to constructive phase. So this is very interesting because the remote sensing can explain the morphological changes of the one object in the surface of the Earth. And next, I would like to share the information about the potential use of the ground deformation related to the INSAR and time series analysis. So related to the INSAR, many papers or many products since 1992 already discussed by Masonet, yeah. we can understand the first interferogram that available in the market, or the scientists or the community, is written by Masonet in the 1992 related to California Landers earthquake. So it's this is the first interferogram related to the ground deformation caused by the earthquake. But in this afternoon, in this session, I would like to share the information about the potential of INSAR based on the time series analysis. So this is more to the left part of the cycle of the natural disaster, related to the preparation or preparedness. So before the earthquake. So the time series analysis, we can understand the ground deformation, how to see the movement of the tectonic, or the movement or the inflation of the one volcano related to the tectonic movement. So based on the time series analysis, we can understand, we would like to study the threshold when we, in terms of predict when disaster will be occurred. So this is a very interesting one, that because work from the Lasetsky in the 2020, they provide services, provide the interferogram freely through the website. So from the initiative called Comet Lixar, so we can download the interferogram. So we already, the interferogram is already processed automatically in the Comet Lixar. So for the time series analysis, we also, we can utilize the LixBus algorithm that provided by Morishita. So this two information is available on the internet freely. So now we can understand, if the friends here who attend this Aperture Tutorial 4, you can try this kind of the data and information available to write a good paper, and we can present it in the Aperture 2021 in the next November in Bali. This is the illustration of the comet, the initiative that from Nottingham University, to provide the interferogram freely in the website. So you can check by Googling this kind of information, the comet and the Lixar. So freely access and freely download. So this is the illustration of the Comet Lixar, the data that's available. So after we go to the website, we can download all the interferogram here that's available. So we can experience to process the time series analysis by using the LixBus that's written by the Morishita. So this is the illustration of the website of the Comet. The Comet itself is the initiative that provides the free interferogram across the active tectonic and volcanic belt. For example, in Indonesia, only in the Sumatra, Java, Nusa Tenggara, Bali, and some part of the Sulawesi and Maluku Island. So this is the illustration of the interferogram that provided by Lixar. Lixar is the automatic machine that process all the sentinel data and then produce the interferogram. So because if we want to talk about the time series analysis, we should have a long-term data observation. And this is, for example, for the sentinel one, it is available from 2015 until right now. So at least we have a 5 years time series analysis. So we can understand the trend, the velocity of the movement related to the tectonic or the volcanic. So for example, this is I would like to share how we process the interferogram for Baribis Fault in the West Java, for example. This is the example of the Baribis Fault near the Cirebon or Majalengka Regency in the West Java. So we can see that there is a ascending orbit and descending orbit. So the Lixar provide the interferogram in unwrapped phase. So it's already unwrapping automatically, because if we use our desktop, for example, by snap, the unwrapping phase is the most problem stage in the data SAR data processing, because it consumes a lot of memory of the computer, of the machine. So sometimes the unwrapping stage in the snap is most difficult, and always sometimes it's fail because the scarcity of the RAM, of the memory of the machine. But by using the interferogram from the Elixir, we get the unwrapped interferogram freely. And then we utilize the interferogram by using the LixBus algorithm, and also it is freely available in the GitHub. So friends that maybe usually utilize the Linux or coding or scripting, we can directly install the LixBus, and then we can get the information, the velocity, the interferogram, the velocity of the fault, for example. So this is the example of the Baribis fault in the West Java near the Majalengka. So we can see ascending the data available in the LixBus. And also this is the illustration of the descending orbit. So it's quite similar of the ascending and descending. And so we can, from this velocity analysis, in the time series analysis, we can understand that at least maybe the velocity of this area is around 7 millimeters here, the velocity. We can see here, the average is around 7 millimeters. And also, this is the one example of the round volcano in the East Java, near the Banyuwangi, in the Ijen, Kawah Ijen. But in the eastern part, there is one volcano there. The name is Round Volcano. And then the interferogram is available in the Elixir website. So we download it, and we process all the interferogram, and also we applied a lot of algorithm, for example, by applying atmospheric correction provided by Geckos from Nottingham University also. And then we can understand the formation before the eruption, because this round volcano has erupted in this early year, in the 2020, maybe in the last February, some eruption occurred in the round volcano. So if we process the data from 2050 until right now, we can see the variation of the velocity in the 1 point. So we can see it is inflation of deflation. If we look in more detail, for example, in the some part around here, so we can understand the inflation and deflation of the some part of this around the crater. So maybe this can be indicate that the magma movement, we can model it by maybe, for example, MOGI model to understand where is the magma, how volume in there. So sometimes this is a very basic information that provided by remote sensing, especially from SAR data. So our team right now try to write a paper and already submit an abstract to the Aperture 2021. Maybe we collaborate with the friends from the PVMBG to assess the advantage of the SAR image to understand the before and after of the round volcano eruption in the 2021. So maybe hopefully we can success to validate with the ground data, because our friend from Volcanological Research Institute or PVMBG in Bandung have a lot of observation station around this volcano, and then we would like to improve our model by validate by using the GPS observation around this area. Hopefully we can success, and hopefully we can submit the paper before the deadline in the May 31st, as already mentioned before by Professor Josaphat. So this is just my sharing today. Thank you very much for your attention. And yeah, we would like to invite you all to utilize all data available free For example, the SAR data from Sentinel is free, so it needs your creativity to choose what kind of the event, what kind of the natural disaster, for example, if you are interested. So you can process all the data by software that available, maybe from Snap, and then you can submit the abstract and then write a good paper in the before the May 31st, 2021. And also, as Indonesian Society or Remote Sensing or MAPIN, we would like to invite you all to join to our organization here to share, to update all the information related to the remote sensing and its application. So right now, we already have many commissariat from all the good big cities in Indonesia, across the Indonesia, from Aceh, and then the eastern part right now is from to Manado, or so North Sulawesi. Right now we have organization in the Gorontalo, and then Sulawesi Tenggara, Sulawesi Selatan, other things. So we can provide many services, or by improve the competency, by join the MAPIN, and also we have a journal MAPIN. If you are interested, just Googling or go to our website, or maybe many YouTube, because many information that already published, we put it in our social media, for example, in the YouTube. So a lot of tutorial or talking webinar, we already put it in the YouTube of MAPIN channel. So this is my share today. I would like to acknowledge to Asia, European Space Agency, by Copernicus program that provide the Sentinel data free. So we are very happy to utilize all the data from Sentinel program, and also to Comet, Lixar, Geckos, and Lixbus, and also all the papers that are noticed from Morishita, and then from Lasesky, from you, and other things. And also big appreciation for you all the participants here for this tutorial this afternoon. Thank you very much, and I would like to give back again to the Dr. Sanjiwana. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh, and good afternoon.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Dr. Agustan, for the interesting presentation from the start of the remote sensing explanation, the basic until the application of SAR technology for disaster monitoring. And right now we have 4 questions, and we have only 10 minutes, so maybe we can cover all, but if we cannot cover all of the questions, we can submit the question to Dr. Agustan later on to be replied. So the first question is, as you mentioned in the slide, horizontal displacement from SAR images. How can we extract the horizontal displacement from the line of sight information from SAR data? So maybe...
yes. Okay. Yes. From the ground deformation, we only have which we call line of sight displacement. So by the trigonometrical method or trigonometrical modeling, we can map the line of sight displacement into 2 components, horizontal displacement and vertical displacement. For example, for the horizontal displacement, we utilize the sinus function. We map to the vertical to the horizontal by sinus function. To map the lines of sight displacement to the vertical, we utilize the cosinus function by divided cosinus, the target of the inclination of the orbit of the satellite. So the horizontal and the vertical displacement, we got it from the model. So that's why we always, we still need the validation from the ground truth verification from GNSS observation. That's my answer.
Okay, thank you, Dr. Agustan. I hope it answered the question of the questions. So we have another 3 questions. So the second question is, INSAR data in Lixar website always updated?
In which one? In which website?
Lixar.
Oh, Lixar.
Yes.
Yes, in the Lixar, because they provide in the whole country. Sometimes the data it delay 3 months, but for the natural disaster itself, not for the time series, yeah. For the natural disaster, for example, if there is a big earthquake, sometimes in the earthquake section, they provide the data if the data available from the Sentinel. So from the Sentinel to provide the unwrapped interferogram, sometimes it delays 3 months. But for the big occasion of the one event that occurred, sometimes they provide in the near real time. So directly we can check. Yeah, because we are in the user segment, we don't have any authority to ask them to provide for us because it's free. So this is the disadvantages for the data or the system that free available. So if we want to make it our itself, maybe yeah, so we can process by ourselves itself. That's my answer.
Yes, thank you. I think that will answer the questions. So other question is, do you have the application of SAR for detection oil spill?
Oh, yes. For the oil spill detection, we can utilize the backscatter image. Only one polarization is enough. So the oil spill can be detected easily by SAR image. For example, in the Montara occasion or in the Singapore occasion in the Batam. So it's very clear to detect by the SAR image because the color itself is very dark compared to the natural or common sea. So can easily to detect the oil spill by backscatter image of SAR data.
Okay, so I think that's possible to be conducted using SAR data. The other question is, how effective is the SAR data for disaster monitoring? SAR data sometimes available sporadically, so not all of area of interest are covered. So how effective is the SAR data for disaster monitoring, because not all of the area will be covered by using the radar data?
In my opinion, the disadvantage of the remote sensing is a temporal resolution, yeah, compared to the natural disaster, because disaster is occurred suddenly. We cannot estimate when and then where. We cannot make a schedule of the satellite to observe before the disaster, for example. So, it depends on the data available, because the satellite-based remote sensing or satellite-based SAR data, it has a temporal resolution that already distinguished. It's already determined. So we cannot get the data from, for example, if we need it in the emergency response, yeah, for example. So that's why we must combine with the other platform, especially drone right now. The drone technology is very mobile and very easy to detect for the emergency response. That's my opinion.
Okay, thank you, Dr. Agustan. So the temporal resolution is plays role for the availability of the SAR data. And there are two more questions. Does LixBus running in Linux only? How is the max baseline perpendicular in LixBus?
Oh yes, because LixBus is written in the shell script, so it runs in the terminal, Mac terminal or Linux, and then the maximum perpendicular baseline is not restricted. We can change because it's a open source code, yeah, so you can modify by yourself. So the interesting to join of the GitHub community and then to discuss for example, this community, we can understand the flow and then we can modify the coding. The code itself depends on your imagination. So that's my opinion.
Okay, thank you, Dr. Agustan. So maybe this one is the last question. It's regarding the Mount Round deformation. How many images did you have downloaded, and how is the size of each interferogram images?
For your information, we downloaded the data available from 2015. Yeah, usually in average 500 interferograms. Usually in the one range of from 2015 until 2017. But after processing by LixBus, because we must excluding the outlier, the noise and everything, sometimes the interferogram reduce up to only 100. So from 500 interferograms reduced to the 100, and so we can understand there is a gap during the time to time. So because it's related to the noise. This is my answer.
Okay, thank you, Dr. Agustan, for the explanation. So I think we have reached the end of your session. Thank you very much for the explanation, and I hope we can see you in the Aperture conference. Thank you very much, Dr. Agustan.
Okay, thank you very much, Dr. Sanjiwana. Thank you very much, and see you all guys in the Aperture 2021 in Bali. Thank you.
Okay, thank you, Dr. Agustan. So for the second session, I will check for the second presenter if he is already here. So the second presenter is Dr. Adriano Meta from MetaSensing, Netherland. Have you are available in the room? Are you available? Not yet. Okay. Okay. While waiting for the second presenter, we will check if the third presenter is already here. Dr. Marwan Younis. If you already here, please, you can open your mic. Okay, not yet. Dr. Marwan Younis or Dr. Adriano Meta? Okay, while waiting, there is another question. Actually, if Dr. Agustan may, you can open your mic again. There is another one question from the attendants, from the participant. Dr. Agustan, if you still here, masih mungkin ini. Dr. Agustan. Oh, okay. Yes, we still have one question for you while waiting for the second presenter. So I hope you don't mind. So how effective or potential the SAR data for analyzing drought for agricultural application?
Oh yes, SAR data for the agricultural application is very potential use, yeah. Because for example, our friend from Ministry of Agriculture already utilize the ELOS2 data. They can easily identify the cycle of the paddy field from land preparation, from vegetation stage, from generation stage, and from the up to harvesting. Because the most powerful SAR data, you can identify the wet area, the wetland. So because the water or the wetland is can be easily identified by SAR with the black color, and then we can see the area that already flooded during the land preparation. And also if we utilize the dual polarization, you can understand the phenological height of the paddy rice or the paddy, of the paddy. So the phonological states, you can distinguish between the vegetation up to the harvesting. So many papers already published related to this one. Our friends from Lapan, from Ministry of Agriculture, Bu Sasa, for example, is already utilized the SAR data for the agriculture, especially for the paddy field and the paddy phenological stage.
Okay, thank you. I actually interested in the is it possible to combine the ascending orbit and descending observation for like an application for disaster or maybe other application?
By combining ascending and descending, actually we get the information of the deformation in the more accurate way. For example, as we discussed before, from line of sight displacement, you can model the horizontal and vertical. But if you have ascending and descending, so maybe you can understand the three-dimensional model. So by intersection of the ascending and descending, because the direction is quite opposite, so you can have the absolute value, for example, and then you must validate through the ground truth by GNSS observation.
Okay, yeah, I think that will be interesting to explore. Yes. Oh, we still wait for the second or third presenter. If other participants have more questions, I think Dr. Agustan is more willing to answer the question because we still have extra time with him. So please, if you have any question, just write your question on the link, or maybe you can just open your mic. Maybe it's possible to do that in Zoom if you may.
So maybe we can explore all the data available, all the technique available during the GitHub community. You can modify your script. It is very challenging, yeah, for example. So maybe Pak Ilham with his student in the Hasanuddin University can assess his student to process in the certain area, for example. If you see the website of the Comet, you can see a lot of area, yeah, the code of the area. So maybe one student, one scene. So you can understand, you have experience how to run the LixBus method to see the time series analysis related to the velocity of the tectonic. It's quite challenging.
Is there any plan for from the BPPT or maybe MAPIN to provide the interferogram images for Indonesia continuously available?
Yeah. Maybe if we have a good machine, yeah, maybe, for example, yeah, that's why maybe. But right now it's already taken by other institution, yeah. So maybe we must have a good positioning that area that not yet done by other people. Yeah, this is a good idea. Hopefully we can do that.
Okay. Yeah, I think maybe many people will try to access the data.
Yeah, because the trend is the cloud computing, big data analysis, collaboration. The trend is there.
Yes. Okay. For the big data analysis, do you still consider to use the Earth Engine or EO Factory? Maybe have more advantages compared to the Google Earth Engine application?
Right now, our friend here in BPT already try to access the Earth Observe AO Factory and already GEE and also the Amazon. But for example, the EO Factory, because Pak Farhan just provide us around 200 tokens, so maybe it's already run out, so we don't have any experience anymore. But it's quite interesting, yeah, and quite fast, the information. Compared to GEE is free, yeah. So right now we have application in our portal in the neonet.id. We already success to process the Sentinel-5 automatically. So in that portal in the neonet.id, you can get the image of the carbon monoxide gases in above the Indonesian atmosphere. So it processed automatically by GEE. The main machine is GEE, and then we put it in our portal, and then we put it in the free available. So our effort there to provide all the data free, and we put it free also.
Okay, that's good, I think.
Please check and make comment.
There's one question here, actually. I am new in SAR data, but really interested in analyzing the ground deformation for landslide. How to start learning and where I can find the tutorial for analyzing SAR data.
Landslide is the derivative disaster related to the hydrometeorology, like high rainfall, the stability of the slope, steep slope, and the geological setting, and so on. So maybe for the landslide, we must combine with the other science and technology, other information. And if we understand the mechanism of landslide, we can put the part of the SAR data in the right part, yeah, because the SAR data can detect the topography and the deformation, and maybe for the image itself to understand the moisture of the soil. I think so.
Do you have any suggestion to how to start learning SAR, maybe SAR application, how to process the data? Do you have any source that maybe can be accessed?
Oh, yes. In the first, maybe you can check the Mapin YouTube, Mapin channel. Yesterday we have a webinar. We have a tutorial how to download the data and how to process the SAR data by using a Snap. It conveyed by our friend Ibu Fauzia Al Hasana from BPPT also, and it's already available in the YouTube, which we call webinar 19, series 19. The title is Citra SAR and related to the geological interpretation. So please check there. And many sources, yeah, not only in the our mapping channel, but in the YouTube you can find a lot of, but maybe in English, but maybe in Indonesian language is by Bu Fauzia. So please check and make comment, subscribe and like.
Okay, that's a promotion.
Yeah, you promote.
Yeah, you can follow the
Mapin, Apisar, and all things we can promote here.
Yes, you can follow the Mapin channel in order to learn about the SAR application and also SAR processing. There's another question, if you don't mind. If you don't mind, is the SAR data effective to use for the regional spatial planning or RTRW?
It depends on the map scale. If we for regional planning for the large scale, I think not quite good, yeah, because the spatial resolution of SAR data at least 10 meters resolution. Maybe for the detailed regional planning, I think need large scale map. For example, 1 to 5,000, yeah, 5,000 scale map. But for the topography, I think SAR data should be used, because if you want to make a good regional planning, you must consider the disaster hazard, yeah. So the disaster hazard can be easily identified maybe from the SAR image, because you can see the geological setting, the fault on the things. So you can see the steep slope or identify other related morphological area. So I think SAR should be one of the complement to make a good spatial planning.
Okay.
That's my opinion.
Okay, thank you, Dr. Agustan. I think we already have the second presenter here. Thank you for your extra time answering the questions. Thank you very much.
Sip.
Okay, I would like to call the Dr. Adriano Meta. If the presenter is already here, you can open your mic. to Dr. Adriano Meta.
Yes, hi,
Hi.
good afternoon.
Good afternoon.
Actually, I'm Simone Placidi from MetaSensing. I made a mistake with the timing. So I told, I'm very sorry, I told
right.
Adriano Meta, I thought GST was Jakarta
Okay.
time.
Yes.
So actually I contacted him and yeah, I can start and
Okay.
then see if we can manage.
Okay.
So I was trying to add the background.
Okay.
Okay, with my background.
Thank you.
I can let me share the presentation. I'm very sorry for this misunderstanding.
That's all right. I will introduce a brief introduction of Dr. Adriano Meta. Yes.
Yes.
So Dr. Adriano Meta from MetaSensing graduated from the University of Rome in 2002 and got the PhD from the Delft University of Technology in Netherlands in 2006. And he right now he is the director of the MetaSensing in Netherlands, which he founded in 2008. So for Dr. Adriano Meta, the time is yours. You have 45 minutes to give the presentation. Thank you.
Okay. Okay. As I said, I will present on behalf of Adriano Meta. So I'm Simone Placidi, and I'm actually the responsible for MetaSensing in Asia Pacific. So I'm gonna show you actually today our Airborne SAR systems and its applications. So I'm gonna show you a brief overview of MetaSensing and different platforms for SAR systems, and then the Airborne SAR systems, how it's actually working. And then I will give you examples overview of the Airborne SAR systems and its application that we have. So the goal of this presentation is to provide overview of airborne SAR systems and the application for these systems. So MetaSensing is basically SME, so a small medium enterprise with a unique and comprehensive expertise in the development and production of synthetic aperture radar systems. So we were founded in 2008 in the Netherlands within the European Space Agency Incubation Center. The goal was to develop the first high-resolution compact airborne SAR systems at X-band. And then we opened other offices in Italy, in Singapore, and in Korea. So our vision is to offer high quality, compact, easy to use, and platform agnostic innovative SAR sensor, and to be the first SME providing a full range of SAR sensors for ground, airborne, and spaceborne platforms. So our mission has been always to enable the geospatial community to operate their own advanced SAR systems to collect valuable geospatial information. So supporting with supply providing the airborne SAR systems. We have actually different business models to support different users. So MetaSensing can deliver the complete end-to-end system to the clients, which can be either something already developed or a custom development. We execute SAR data collection and all the data processing to deliver only the results. And then we offer also the technical assistance to support SAR capability building and new developments with partners. And we also sometimes offer a transfer of technology or knowledge from our in-house expertise and know-how. So we have a complete, basically in-house technology capability to go from the consolidation of the requirements through the design engineering, so manufacturing, assembly, integration, and testing of radars, and then all the verification, which we do it either from our aircraft or from lab and field verification. We are actually focusing on three different sectors. One is geomatics and weather, so it's more a commercial sector. The other one is defense and space. And then we have a R&D department, which spans through all the three sectors. We have different products. Some of them are SAR, like Fast GBSAR, StarSAR-X, Guardian, and the SAR simulators. But today we are going, I'm gonna show and talk about the MetaSAR family, which is our airborne SAR systems. So, as you know, there are, let's say, SAR needs a moving platform. So this platform can be actually in different altitudes from the ground, depending on where you install the SAR system. You have different responses, different characteristics. So you can have a ground-based SAR, which usually is installed on a linear rail. So on the linear rail, and this actually is, it can provide, for example, movements in front of the radar. Well, the good advantage is actually that you have very high revisit cycle. So you have one image every 10 seconds, for example. The problem, the drawback is actually that you have only a limited field of view. So if you want to increase actually the coverage, you can move to use airborne systems, which can be a drone-based SAR. So you can use it for covering, for example, a full open pit mine. So a relatively small area, but still a bit bigger than the ground-based SARs. And also the revisit time is quite flexible depending on the UAV that you install it on. And this actually provides basically a smaller coverage. While if you want to increase the coverage, you can then move to airborne SAR systems. So they can provide regional mapping or nationwide mapping, because you have an aircraft which flies over the area of interest. You can have basically different view angles, different geometry to acquire your data. And then you have also flexible revisit time. If you want to increase still more the coverage, basically, you can go to satellite platforms. And then, of course, satellite platform can provide a worldwide mapping. So basically, with one SAR on satellite, you cover the whole Earth. Of course, the revisit time for one satellite is limited to a few days. And for example, there is some drawbacks, which has a limited viewing angles, for example. So flexibility is also affected. For example, once the satellite is launched, the satellite is there, so you can't do much of maintenance or recovery of a system. So these are actually the four main actual platform where you can install a SAR system. And today we are going to focus more on the airborne side. So actually the airborne airborne SAR is basically a complementary technology to the satellite SAR. So of course, each one has its own advantages and limitations. It depends on the application, on the use, on the need of the data. So while of course satellite SAR has a large coverage, has a ease of operation once it's in orbit, at the same time it has a bit of let's say limited frequency bands, for example. So far, L-band, S-band, C and X have been launched and used in space. Resolution is also a bit less than airborne SAR. Sensitivity, all the revisit frequency, the viewing geometry is limited to basically the satellite orbit. And it's so far, there's not yet really a multi-frequency system, for example, and the development and production costs are higher than airborne SAR. At the same time, the airborne sound system, basically you can develop any frequency band, so you can fly any of relevant SAR frequency bands, so UHF, P, L-band, S, C, X, KU, KA, and you can also combine this frequency into one aircraft, for example. You have flexibility in the observation and configuration geometry. So you can look at the north-south or west-east, bistatic and multistatic observations. You can have a very high resolution, for example, from an airborne SAR, high sensitivity, and a higher revisit frequency as well. Of course, there's a limitation which relates to the area coverage and the area to monitor. So basically, you are limited to look at the area where you are flying over. So you cannot have a full Earth covered. But if you're looking at national, for example, national mapping, that's enough to have airborne SAR. Installation also is a bit, well, limited. It's a bit, also the operation, you need to ask, for example, permission to fly compared to the satellite that once it's in space, it's ongoing. Every time you have to fly, you have to ask permission to their traffic controller, for example, to fly. The cost for a development and production are lower than a satellite system. And the advantage, one of the advantage of airborne SAR is actually that you can use it to demonstrate basically your future satellite SAR system or satellite SAR concept. So you can acquire, you can develop your airborne SAR demonstrator. You can acquire data with that in preparation to a future satellite mission. So as I said, today we, let's say, through MetaSensing systems and experience, we are going to look at the airborne SAR systems and application. And for example, our system have been installed on a lot of different aircraft platforms, going from a very large one like Orion P3 from the US Air Force to smaller system like platform like General Aviation Cessna 208 or Kodiak, Piper, or even rotary wings, so helicopters, or drones, so fixed wing or rotary joint drones. So having a compact airborne SAR allows to have easy installation and also easy data collection of SAR data. Here is an example, for example, of installations. So we install it on the nose of an aircraft or on a lateral door or on the bottom of the aircraft or on the bottom of a helicopter drone. So depending on the application, on the data requirements, on the requirements on the viewing geometry, there is a flexibility to adjust the installation on a lot of different aircraft. So in this way, you can still have SAR data to use. So basically, airborne SAR system is composed of two main sides. One is the airborne segment, which includes basically the equipment in the aircraft, which is composed of the SAR sensor, so with all the electronics, so control computer, waveform generator, ADC, all the RF part, the high power amplifiers, GPS, INS system, and all the disk for data storage, including then the GPS antenna and the RF antennas, and the laptop for the operator to control the system. If it's installed on an unmanned platform, the operator actually is on the ground. And next to the airborne segment, there is basically the ground segment where you process the data. So usually you record the data on board, you bring them to the office, and then you process this data, providing calibrated, geolocated single look complex images from the acquired raw data. There are two different, basically, SAR focusing algorithm types. One is a time domain, one is a frequency domain. All of them have different features, characteristics. And MetaSensing, we use time domain and a global back projection to focus the SAR data. With a global back projection, we can exploit all the parallel processing power with the GPU-equipped workstations. So we have a scalable SAR processing with multiple GPU cards or multiple GPU-equipped machines. So that actually the processing time can be reduced. And then, of course, you can process the data accordingly to the requirements. And just to go a bit in detail, basically we have the radar raw data, which are range compressed. So we have the range Doppler maps, then together with the navigation data, which have been post-processed and synchronized to the raw data, we apply all the back projection. So the focusing of a single look, the data to get the single look complex on a preloaded digital elevation model. After the single look complex, we can take care of all the calibration, like a range delay calibration, radiometric calibration, and then we can generate all the single look complex, which are geometrically and radiometrically calibrated. So these two sides, so the airborne segment and ground segment, compose basically the airborne SAR systems. Basically, how do we select the right frequency for a different application? We know that different application needs different radar frequencies. And that's because the wavelengths interact in a different way with the medium, with the scenario and the target. So for example, Another reason, it's actually depending on the penetration required. So the lower frequencies, they have more deeper penetration than higher frequencies. And then, of course, on the image resolution. So if we start from 35 gigahertz radar frequency, for example, we see that we have no penetration depth in the medium. We can have very high resolution data, and being very sensitive to small details, we have a kind of a optical image, an image, a SAR image which resemble the optical images quite a lot. While when you go lower in frequency, so Ku band, X band, C band, L band, P band, and VHF, for example, you gain a lot of more penetration, for example, at P band or at VHF, but the resolution becomes lower. So you don't have such a high resolution images, but you being sensitive to larger features, you are able to penetrate the forest, for example, to look at the ground below the forest, below the trees, and so you can use it for example, the retrieval of digital terrain model below the forest, or detection of targets under the trees. What happens actually in a lot of application is that it's preferred to have a dual frequency system. So you have you can combine a high resolution, so a high frequency system with a low frequency SAR. So in the same aircraft, for example, you can have a system which is a dual frequency with X and P band. So you can use it to generate digital elevation models. So you use a X band for a digital surface model and a P band for a digital terrain model. Or you can have X and L. So again, you use a interferometric X band for a generation of a digital surface model, and L band polarimetric mode to have automatic classification. So then when you combine the data, you retrieve, for example, a land cover classification and the digital elevation models. At the same time, you can have a KU and X band. So this one is mainly used to monitor ocean surface currents or snow. Or you can have KU band and L band that you use to monitor cryosphere. So you can use it to monitor snow or ice. Having a L band, being the L band low frequency, so longer wavelength, they can penetrate through ice or dry snow more than KU band or X band. So at the same time, within the same flight, you can have data of the top of the surface of the ice and also the deeper layers of the ice. And then you can have, for example, LMP, special configuration if you want to study really like biomass or forestry. So all this frequency needs to be selected depending on the application. And this is actually an example of a SAR sensor that actually a list of sensors that we have at MetaSensing and that we have been using for a lot of different applications. So we go from a low frequency P band, which can be used for foliage penetration, so generation of digital terrain model, penetration through sand, change detection for pipeline monitoring, for example, for a differential interferometric SAR. And then slowly we go to higher frequencies. So L band, C band, X band, Ku and Ka. So having an airborne SAR, it allows you to have always a resolution higher than 1 meter. So you can go around, let's say, 75 centimeters for low frequencies, and then higher up to 15 centimeters for a Ka band, for example. And then, as I said, all these systems can have their own GNSS IMU embedded. They are modular and scalable, so you can plug in and combine different frequencies. They can be configured in a multi-static bistatic mode, and then you can acquire all this data and then process them to generate the SAR images. So if you have a dual frequency, you have a SAR image, two SAR images co-located with a different frequency. So this actually shows a list of campaigns we have been running mainly for, let's say, European Space Agency, some for NASA and Environment Canada, which makes use of all the combination of these radar frequencies. So, for example, there was a campaign which need to study the snow water equivalent. So we had a combination of X and Ku band in a fully polarimetric mode. Or, for example, there is actually the BELSAR program, which is a L band, fully polarimetric, interferometric, and with acquisition in a bistatic mode. So with two aircraft. Then there was a NORSAR, which was a C-band with a multi-baseline interferometric configuration. There was SNOW-X, again, to study the snow water equivalent, X and Ku. If you want to study soil moisture, we ran campaign at the L and C band. So we have all these campaigns, which most of them for now are being used for future satellite mission studies or to study possibility to launch a companion satellite for Sentinel-1, for example. However, probably, let's say, in the future, some of these can have also a more commercial application. And for example, these two projects, Oscar and Kaiser, where they see the development of two airborne SAR systems, one at Ku band, one at Ka band, are both for a future satellite mission demonstration. So now I'm going to show you, I'm going to go a bit more in detail on the bistatic campaign called BELSAR. And here, this one was a campaign that we ran a few years ago over Belgium. And the goal was to execute this multi-mission airborne SAR campaign with bistatic and polarimetric interferometric measurements at L band to verify the suitability of launching a companion satellite behind SAOCOM. So we flew actually 5 times every month during the one growth cycle of crop, because the end application was to study the growth of vegetation and crops mainly. So as you can see, we have developed a bistatic SAR system, so we could fly the 2 SAR sensors in 2 different aircraft, completely independent systems. And we could fly to acquire basically fully polarimetric data in monostatic and bistatic acquisition. And at the same time, we could acquire interferometric data, so cross-track and a long-track interferometric data. And because so each system had 4 channels, so basically each system had 2 transmitters and 2 receivers simultaneous. Being able to alternate pulse by pulse the transmission of each transmitter, we could get out 8 different SAR images for each system. This actually is a SAR image, so an example of a bistatic SAR image acquired during this campaign. And here I'm going to show you basically the 4 channels image, so the polarimetric signature results for a monostatic mode. So in this case, the transmitter and receiver were on the same aircraft. In this case, actually the acquisition were run in cross-track. So the 2 aircraft were flying next to each other, and they were separated by 25 meters. So the acquisition were polarimetric and also interferometric across track. And then we had a long track acquisitions. So basically we were flying one after each other. So the aircraft was one after each other, looking at the same area. And that we could also acquire the SAR images in a fully polarimetric mode. So horizontal, horizontal, vertical, horizontal, horizontal, vertical, and vertical, vertical polarization. Another application that actually you can use, where you can use the airborne SAR systems, it's for digital elevation model generation. So basically you can use XMP, so dual frequency system, which can be configured in a polarimetric mode for P-band and repeat pass, or single pass interferometric mode at X-band. In this way, you can get data which are suitable to generate a digital surface model using a single pass interferometric X-band, digital terrain model using the repeat pass P-band. After that, together with the ORI images, you can actually feed the data to generate topographic maps. This one actually is the insert processing flow that we apply. So basically you always start with 2 channels. So 2 radar data channels, which are range compressed. Then they go through all the focusing algorithm, back projection. You have the 2 single look complex images, which are then calibrated. And then you can apply the interferometry on that. For example, multi-looking and phase unwrapping. And then you can obtain the phase to height, basically, conversion that after calibration, it gives you the WGS84 height. So all the heights that you can use to generate digital elevation models. And after that, that information can be fed to any GIS software to create the large mosaic.
Dr. Simon.
Yes.
Sorry, maybe you only have 2 more minutes. Is it okay?
Okay, yes, I go fast. Yeah, this one actually is a comparison between the airborne generated digital elevation model and the digital elevation model from SRTM, and you really see the difference on the SAR, so on the resolution. So you have more insights and details in the elevation model from the aircraft. Another possibility to acquire data at P-band, for example, is to use tomography, so tomosar. So basically, you can get a scan through the forest, so you can have information of the different levels through the forest. So from a ground level, 10 meters above the ground, 20 meters above the ground, and on top of the forest, for example, with these tomosar acquisitions. And this is actually an example of a generation of tomosar DTM and tomosar canopy height. So from same aircraft, several flights, you can get out this information. Another application while using L-band, for example, is to have collect airborne fully polarimetric SAR data at L-band, which are radiometrically calibrated with a high resolution and generate single look complex. These single look complex data are provided to a third party, commercial third party, and they basically retrieve water leaks. So through the utilities pipeline. So applying SAR different, let's say SAR retrieval, they are able to pinpoint water leaks in the utilities pipeline. For example, MetaSensing has been used to monitor forest. So again, this was a campaign supporting the study of having a satellite next to Sentinel-1 to monitor forest. This one again was a single pass interferometric system with a multiple baseline, which could provide information on basically two different baselines, giving more sensitivity to different height, and then to retrieve basically the forest height. So really information on the ground and the top of the forest. X-band used for high resolution imaging. For example, we flew a campaign. We covered 100 kilometers square 12 times in 2 days over the city of Rotterdam. And this one was to monitor actually, to have a time mapping, basically difference in actually all the harbor movements and urban scenarios. As I said before, we can use XL, so X-band in interferometric mode to retrieve digital surface model, and L-band for in a polarimetric mode. And when you combine them together, you can get out a land cover classification. These are examples of collocated SAR images, X and L. So this one is a L-band, this one is a X-band, and you see the different backscatters. And this one actually is a composite of X and L together, where actually you can see different features. Another application from Airborne system is basically the studies or measurements of terrain change dynamics. So you can use differential interferometry or amplitude and coherent change detection from drone or airborne, and this can be used to monitor infrastructure or coastline for disaster prevention, for example.
Dr. Simon, I think the
Yes.
time is up. Sorry.
Yeah. Okay. Yes. Yeah, I'm done. That's fine.
Okay.
I can go through that.
Thank you very much for the very interesting presentation. Actually, we have so many applications that can be conducted by the platform provided from MetaSensing. Dr. Simon Placidi is the Asia Pacific Area Manager for MetaSensing, if I'm not mistaken.
Yes. Yes.
Okay. And we have the explanation a lot of about the mission of the MetaSensing provided. including also the bistatic and monostatic polarization, how to use the data for many application, water leakage and tomosar, and forest mapping. Yeah, it's really interesting to be follow up in the real in other area maybe. So we have one question from Adin. Two questions actually. The first one is, does the Guardian product still need to be processed or ready to be used data, since the Guardian data is a real-time data as you mentioned? So maybe you can clarify the use of
Yes.
Guardian data.
Well, the Guardian system is indeed a real-time system. So it's the data are processed on board. So there is no need to process them. So it's actually a real-time system which provides information in real time. Of course, data can be saved and processed afterwards, but it's actually a real-time system which provides information in on the screen in real time.
Okay, thank you very much for the explanation. I hope it answered the question from Adin. The other questions, is it possible to access the sample data from MetaSensing for research purposes?
Yes. So for a lot of airborne SAR campaigns from the European Space Agency, the data are available in the European Space Agency portal. Otherwise, we have other campaigns data that can be provided. Yes.
Okay. Okay. We still have one questions. How to extract the information from P-band, L-band, and C-band polarimetric for estimating the biomass? Maybe this one is force biomass.
Yes. So, okay, for a biomass, more, let's say at least what we have been using, it's more interferometric. So basically, we look at the altitude, the height of the forest through the interferometric data, for example. So as a meta-sensing, we provide all the systems, basically, and data processing up to level 1, let's say, level 1C. And then all the derived products usually are taken care of by partners or scientific community. So for example, for this activity, the C-band, interferometric C-band with multi-baseline, we were able actually to get the exact interferometric height between the digital terrain model and the C-band phase center in the aircraft, and to retrieve basically all the height maps of the forest. So what we did is actually flying over time. So every month we flew, and then you have basically the same information of a forest height, but at different point in times. And then you can relate that to study how the biomass develops. So that's actually some biomass studies.
Okay, thank you very much for the explanation. And that I think this one is the last question for this session. Can you give some information about the bandwidth that you use to achieve the 0.75 meter resolution for airborne L and P band?
Sorry, what do you mean? Let's say we use, sorry, again.
Could you
Wow.
Could you give some information about the bandwidth that you use to achieve the 0.75 meter resolution?
Okay, well, we use 200 megahertz bandwidth. So we have a 200 megahertz transmitted bandwidth for a slant range resolution of 75 centimeters. Of course, this is actually what we usually, let's say, what our system is capable of. But a lot of times, especially at P-band, you have restrictions in the allowed bandwidth that can be transmitted. So by the authorities, they probably, most of the time, they don't allow to transmit 200 megahertz. So you have to narrow down the bandwidth, transmitted bandwidth. And then, of course, you will degrade the slant range resolution. Usually around 1 meter, it's possible. Okay, it depends also on the location of the acquisition, but for, let's say, slant range resolution, instrumental bandwidth is 200 megahertz. But then in operations, you need to look at the permission to transmit, and of course also RFI, if there are radio frequency interference, which enter basically the data. And then you have to take care of that. And then if you have to remove some part of the spectrum, then of course your resolution degrades.
Thank you very much for the presentation. Actually, is it possible to access the information from MetaSensing? Can you provide the information, or maybe website eme?
Yes. You can well, you can look on the website. Otherwise, you can send an email to info@metasensing.com, and then we can reply. Or if you want, you can write directly to me as well. That's also fine. But yes, that's all possible.
Okay, thank you very much for your time, and it is really a quite interesting presentation. Thank you very much once again.
Thank you very much, and apologies again for the delay and my mistake.
No worries. Time can be really confusing.
Yes, too many time zones.
Thank you, Dr. Simon Plasidi.
Thank you. Bye.
So for the third presenter, I would like to invite Dr. Marwan Younis. If he's already here, you can turn on your camera or turn on your microphone.
Yes, hello.
Hello.
Yeah,
thank you very much. So before the presentation will be started, I would like to introduce Dr. Marwan Younis. So Dr. Marwan Younis received his BSc in Electrical Engineering from the University of Baghdad, Iraq in 1992, and in an MSc and PhD degree in Electrical Engineering from the Universität of Karlsruhe, I don't know if I mentioned it right, Germany in 1997 and 2004. And he is now working as the head of the SAR Technique Group at the DLR, the German Aerospace Center, and professor for the Spaceborne Radar System at the Karlsruhe Institute for Technology in German. So for Dr. Marwan Younis, please, the time is yours for 45 minutes.
Okay, thank you very much. I hope you can see my screen.
Yes, we can.
Okay, and I'm just activating the chat. Thank you very much for the introduction. So we do it a laser pointer. It's an honor for me to be presenting at the tutorial series for the Asia Pacific SAR conference, or the pre-tutorial series for the Asia Pacific conference. And thank you for the introduction. You already see kind of the organization that were mentioned before. So this is the DLR where I work. It's something like the German Aerospace Center. I'm also at the University of Karlsruhe, or the Karlsruhe Institute of Technology, where I teach. And the motivation for giving the course today is actually comes from the IEEE GRSS, which is the Geoscience and Remote Sensing Society. And as one of the activities that we do there is to give lectures and series to try to promote the geoscience and remote sensing. So these are the logos that you see over here, and obviously the main topic is the AP SAR itself. Let me give you some short overview of the topics today. What I want to do is basically only it's only one topic. I want to explain the principles of synthetic aperture radar. This is going to be a combination between something like signal processing, only a little bit, I'm going to explain this, and the instrument. So I'm not so much looking at the application, what we do with the synthetic aperture images after we get them, but I'm more interested how this works. And this is what I'm going to try to explain to you today. There are some participants over 100, so maybe it's going to be difficult to have something interaction, but I'm going to try to do this a little bit. Also, please, if you have questions, just write them in the chat. I'm going to try to look at the chat in between, and if there's a question on something, I'm going to try to answer it. Otherwise, we do it at the end of the presentation. And maybe the last point I was intending to have about 1 hour, but I'm going to shorten it to 45 minutes. This is no problem. This is no problem at all. Good. Then we start by asking the question, what is remote sensing? Remote sensing is whenever you use an instrument to investigate something without touching it. So this without touching it means at a distance. This distance can be a few millimeters. For example, you have a sensor monitoring the wheels of the train. It's very near to it just to see if there are cracks. Or remote sensing is something, if we look at the moon or of the planets from the Earth, and there are millions of kilometers in between. This is also remote sensing that we have over here. The beginning of remote sensing was aerial photography. And I never was sure what this means, so I did what everyone does today. I just looked in the internet, and aerial photography is taking photographs with a camera from an elevated position. And this guy over here, you see, this is the beginning of remote sensing, 1862. It was over the city of Paris in France. And this guy was taking photos of Paris, and this was the beginning of remote sensing. And you can find lots of information about this in the internet. I find this interesting because this was lots of time ago, and now we are going back to remote sensing. Nowadays, you can buy a drone or UAV, and you can put a camera on it, and you can control it with your computer. And we are actually going back to the origins of the remote sensing that we have. This is an example of a camera photo taken, so not radar at all. And I like this photo a lot. What you see here are camels. And if you look at this in detail, you see that what we are seeing mostly are the shadows of the camels. It's not the camel itself. Look here, this is the camel, and this is the shadow of the camel. This is a property of optical images when you use a camera, but we have a similar effect in radar also. The shadows have an important role in radar images, and we also have shadows in radar images. And this is where I'm going to come back to this topic later on. But let's continue about remote sensing and ask ourselves, what are the information that we get from remote sensing? Well, these are spatial. This is the geometric resolution basic that we have, the pixels. Spectral, this depends on the frequency that we have, the frequency that we operate our sensors at. We have intensity. So if we look at an area with an instrument, I know this region gives back lots of energy, the other region gives back very little energy, and very important temporal information. And this is mostly why we use remote sensing today. If I want to see where I live, I look in Google Earth and I see the image of the apartment where I live. But if what we are interested in are the changes, we want to see what is happening on our planet, how much the forests are changing, how much the ice is melting, all these effects we want to see. So we want to see changes, and this means temporal information revisit. We have different types of remote sensing sensors. We have optical and infrared sensors. The Sentinel-1, actual Sentinel-2 series are examples of this. And we have microwave sensors given over here in the image. Microwave sensors very broadly can be characterized into two types. We have passive sensors. These do not transmit anything. They just receive and they process the naturally received radiation of the area which is being looked at. And we have active sensors, which are radars. And today I'm going to be talking about active sensors, basically. These operate at different frequency range. And if you look here, you see the frequencies with increasing values, so 1 gigahertz, 10 gigahertz, and so on, and the corresponding wavelengths over here. And now you can characterize sensors that we have in optical sensors here, where the wavelength is very short. We're always talking about electromagnetic waves, huh? It's all the same, but it's the wavelength which is the different. We have LiDAR, which is a laser sensor, basically. We have microwaves. These are the passive sensors that I just mentioned. And we have our radar active sensors, which operate in the frequency range. And if you learned, were listening to the tutorial before, it's exactly this what was being talked about, from a few hundred megahertz up to a few gigahertz, basically, in the frequencies that we have over here. Everything which is on the top is active. Everything which is on the bottom is passive sensors over here. So all this talking, okay, how does a radar image look as? And this is just one example that you see over here. This is actually Munich. I work nearby Munich, and this is why I chose this image. This was taken by our Airborne sensor. This is what is called Schloss Nymphenburg, and you see the typical phenomena of SAR images that you already heard in the tutorial before. This is the castle itself. Here's the garden of it, and you see that you can get these with quite a good resolution. Here is another example. You know that everything which appears black in radar images means that very little power comes back. And this is typical water, if it's calm, or roads, for example. And the reason is you transmit from here, you have more or less a specular reflection. Most of the power goes in this direction, and very little comes back to the radar itself. And this is why it appears black. Over here, you can zoom, and this is something which is not uncommon for the sensors that we have, and you can see that you have quite a good resolution with these systems. Let's compare to an optical image, and you see some differences over here, which are probably due to the different times when the images were taken, but you also see similarities. These houses over here, you can see in both images. Now, typically radar images are black and white. Why? Well, remember the instrument. You at some point have an antenna, and this antenna is transmitting, and you receive something. And what you receive, it's basically a voltage that you have at the terminals of the antennas. There's no color to this voltage that you get. And now let me contradict myself. You see here both the optical image and the radar image, they are colored. And what we use here in the case of the radar, these are not the natural colors. You see the roofs here appear green, although they're not green in reality. What we use here is polarimetry. And this is a topic on its own. It's basically the direction of the electric field vector that we use. It might be oscillating like this, or it might be oscillating like this. And we use combinations of these polarizations in order to get the colors in radar images. Okay, so let's start talking about radar and radar instruments now. This is not too difficult to understand. We know that radar stands for radio detection and ranging, and the principal idea of it is very, very simple. We have our radar sensor. We transmit an electromagnetic wave by the antenna. We have some objects which interact with the waves. Some of the waves come back to the radar, and this is what we measure over here. This is exactly what we measure. And in Germany, we are very proud because the first patent for radar was done by Christian Hülsmeyer in 1904. This was more than 100 years ago. And the idea behind the patent was an application, and the application was to detect ships in fog on the river of Rhine. And you see this over here. You have a ship nearby, you don't see it because there's fog, you transmit something and you come back and you receive, and so you know that there's something nearby. The interesting thing about this patent is that the company where this guy, Mr. Hülsmeyer, was working, told him, no, we don't need this idea. This is not interesting. There's no good application to it. But this was 1904, and now we, of course, know that we have radar sensors everywhere, basically. Okay, how does it work? What we have a transmitter, we generate power, a high amount of power in the systems that we are talking about. These are kilowatts of power that we are generating. We use an antenna to transmit this power. Basically, we want to illuminate the area that we are interested in. Some of the power that we transmit comes back to the antenna. We have a switch or a circulator, we have a receiver, and we do a data recording basically that we have over here. And after we process this data, this is when we get the images basically. And again, I want to be talking about the instrument that we have here. I mentioned that I work and live in Germany, and in Germany we have a type of radar that we don't like that so much. You see it over here. This is a traffic radar, basically. If you're driving with your car, you have a radar over here. It measures your speed. If you're too fast, a photo is taken of the license plate, and then you get a bill sent home, basically. How does this work? Well, we have the same principle as before: transmitter, antenna, receiver. And what we do is when we transmit the electromagnetic wave, we look exactly at the time when the wave leaves the antenna. Now the wave travels to the object, it comes back, and we also record the time when the wave arrives at the receiver. So now what do we have? We have the time delay, which is something that we measure. We have the velocity. This is known because we're talking about electromagnetic waves, so these travel with the velocity of light. So, and what we want to have is the distance, and the wave traveled 2 times the distance. So this is the quantity that we want to have. The other 2 quantities we know, and by this we can measure the distance to an object. And this is the basic principle of the radar operation. It does not change even if we have very complicated SAR systems and so on. The basic principle is always the same. So let's start with the side-looking radar, and it's called SLAR. And I'm going to explain this, and then we're going to look at the resolution that we get from these sensors. And this is going to be the motivation to explain the SAR sensors that we have. Let's move further. We have our radar, we put it on a satellite, we transmit, we receive, we move further, we transmit, we receive. Obviously, the satellite is moving continuously. This is just a stop and go approximation that I'm showing in the animation over here in order to explain the principle. And again, what do we measure? Well, if we have a terrain, we transmit something, and what we measure is what is scattered back from the terrain. And this might look something like this. I like this image also. It's actually a radar image, and I looked it up once in the internet, and it actually is some area in the moon. It looks like a smiley. I like it a lot. So what is the information that we get from this image? We have areas which are dark, which means these areas, for some reason, the backscattered energy from these areas is low. We have areas which are bright, which means we get a higher amount of energy out of these regions. This is what we get here. But coming back, what we measure in radar is something which we call the backscatter coefficient. It's a normalized quantity, and it's the amount of energy that we receive, that we measure by the sensor, divided by the energy which is reflected in an isotropic way. What is this on the denominator? Well, reflected in an isotropic way means it's reflected in all directions the same. So we have a wave which is coming over here, and we assume that we have a scatter which reflects uniform on a sphere, and we divide by this quantity. And the actual, what we measure, we put over here. So it's a normalized quantity. And what this means basically is if we have an area which scatters back into the direction of the radar, then we have a backscatter coefficient which is larger than 1, or in dB it's positive. On the other hand, if we have an area which scatters into a different direction and very little comes back to the radar, then this nominator over here is smaller than the denominator, and the backscatter coefficient is smaller than 1, or negative value in dBs. Okay, so now let's look at this into more details. I just want to explain the geometry that we have. This is the antenna over here. We move in the azimuth direction, which is the x-axis that you see over here. We illuminate an area on the ground. The width of the area we call the swath width. This is the illuminated area. This is the swath that we have over here. And the direction of the propagation of the electromagnetic waves are in the, we call this the range direction. And if you look at from the side, now the sensor is coming out of the screen basically. This is the range direction. The angle between the range direction and the normal to the surface we call the incidence angle. This is the swath width that we have over here. And these are the geometrical quantities that I'm working with today in the lecture today, basically. Also, the sensors that I'm talking about are pulse sensors, which means we send a pulse and then we have a pause where we receive the echo which comes back. And I'm also going to talk only about side-looking sensors because all SAR sensors are side-looking. So we're not looking downwards, but we're looking to the side to some amount over here, which is described by the incidence angle that we have. And now let's talk about the resolution. And the resolution, of course, we might be able to understand it at the size of the pixel that we have. And this has two dimensions. It has in the range direction and in the azimuth direction. And let's talk about the range resolution of a SAR sensor that we have over here. So we transmit a wave, we transmit a pulse over here. And this, we have an object, and the object reflects this pulse back. So this is what we receive over here. And now let's assume that we have a second object which reflects. So we receive a second pulse over here. And the question is about the resolution. How close can these two objects get to each other such that we can still differentiate them, such that we can still know that we have two objects? So if we move too close, these two pulses interact over here and we are no longer able to differentiate between the two. And what I want to do is to actually try to derive this. So just give me a moment. Over here. To derive the equation for the range resolution, I am going to use the equation that you already saw, which you see on the right side over here. And since I have two objects, I want to know the time difference between the two objects. And the time difference is given, this is going to be in red color, but it doesn't matter now. So it's tau 2 minus tau 1. I'm only using this equation that we have over here that we understand. This is given by 2 times the velocity of light. And now I have range 2 minus range 1, basically. And this I'm going to call equation number 1. Now, the question is, when do I reach the resolution limit? Well, this is exactly when the two pulses start touching each other. So the resolution limit is basically reached when the tau 2 minus tau 1 is equal to the pulse duration itself. And the pulse duration is this one, tau p that we have. And in this case, we have reached the resolution limit, which means the difference in the distance is given exactly to the resolution. And this quantity over here is the resolution that we have. Okay. So now we just insert into equation number 1. So then what we get is that the tau p is equal to 2 times C0 multiplied by the range resolution. And this finally gives us the range resolution, which is given by the duration of the pulse multiplied by the velocity of light divided by 2. And now if we look at this, we are not really happy with this result. Why? Well, what this tells us is basically, let me just go further. You see the same equations over here, and the result that we got is this one over here. You see what is happening. If I want to have a good range resolution, I want this quantity over here to be small, because I want to have a good resolution. What does it mean? It means I have two quantities that I could play with. The velocity of light is a constant, so this we cannot play with. What we can change is the duration of the pulse. If I want this one to be small, I have to have a small pulse duration. A small pulse duration means a small amount of energy. This is bad because I if I want to improve the resolution, it means I must make the pulse short. It means I will worsen my signal to noise ratio that I receive because the amount of energy that I transmitted is small. Okay. However, in radar, there's a solution to this, and this is what I'm going to try to explain next. And I'm going to use an analogy first. I'm going to transmit a pulse which has two colors. Assume that I can do this, a red color and a green color. And now what I receive also has a red color and a green color. And what I do now is everything which is green, I will shift by half the pulse length. So I get something like this. I can do this because I receive the pulse, I have it in my memory, in my computer. And whatever is green, I just shift it. So now we see what happens if I have two objects. The pulses over here interact. However, if I do this shifting, I will be able to differentiate the two pulses that I receive, and this means I can improve the resolution. Now we can actually do this, and let me explain this. This is a pulse that I transmit. This is the envelope of the pulse that I transmit. And what I will do is, during this pulse duration, I will change the frequency. So I will change the frequency something like this. And now remember, the frequency and the wavelength are related to each other. So when I change the frequency, it means I'm changing the wavelength, and the wavelength is related to the color in the optical region. In the radar, it's something similar. It's a wavelength which is changing. So this changing of the wavelength means that I do this change over here, and this allows me to compress the pulse, and now the resolution that I get depends on the amount of colors that I have in this pulse, and this we call the bandwidth in microwave engineering. And it turns out, if we do the equation, that the resolution now depends on the inverse of the bandwidth. So if I have a large bandwidth, it means that I have a good resolution over here. This one I can make large, and at the same time I can make the pulse duration also large to get a good signal to noise ratio. So far so good. If you have questions, please write into the chat or ask. And now I'm moving further with this. This equation that we derived of the resolution, of course, depends on the incidence angle. So if I'm looking very shallow, I get this resolution. However, the resolution that I'm interested in is really not this resolution over here, but it's this resolution projected on the ground, because we're typically looking at the ground. So it means I need this quantity over here, so I have to divide by the incidence angle, and we see what we have over here. So depending on the bandwidth that we get, and depending on the incidence angle, the ground range resolution changes basically. And the shallower I get, the further away I move, the better the resolution gets basically. So far about the range resolution. Now let's start talking about the azimuth resolution. And here I need to talk a little bit about antennas, and to make this simpler, I'm going to use the analogy between antennas and optics again. So an isotopic antenna is an antenna which radiates the same in all directions. You can understand this as a light bulb. A light bulb illuminates everything which is around it the same way. Now, all real antennas are directive antennas, which you can understand something like a headlight. A headlight illuminates one region, but leaves the other regions dark. And the same is true for antennas over here. This is, for example, when we have a reflector antenna, we have a concentration of the energy in this region over here, whereas the area behind the antenna is not really that significant or not illuminated. And now the question is, what is the width of the area that we are illuminating? And this we call the beam width. We also sometimes call it the half power beam width of an antenna. And this depends on the size of the antenna. The same as with the headlight. If we have a big reflector in the back of the headlight, we are concentrating our light. And the same happens with an antenna. So the width of this beam in angular units, in radian units, is inversely proportional to the size. But since we are talking about electromagnetics, it's the electrical size. So the electrical size is the physical size divided by the wavelength that we have. And if you're working in electrical engineering and antennas, this is an equation that you should know. The beam width is the wavelength divided by the size of the antenna. What does it mean? It means if I make my antenna big, the beam width gets small, which is good. Or if I make my wavelength short, which means I have a high frequency, I also make my beam width very narrow. Okay. And now with this principle, this is all that we need actually, because now if, because now if I have my radar over here, I have an object over here, I already know that the width of the area that I'm illuminating is the beam width multiplied by the distance, because I want to know this distance over here in meters, which is given by the lambda r naught divided by the size of the antenna. Whereas the range resolution, this is the equation that we showed before, which is the velocity of light divided by 2 times the bandwidth over here. And now I'm going to ask you a question. And if you're fast, you can try to answer this. We have an airborne SAR system, which works in X band, which means at 10 gigahertz. It has a bandwidth of 25 megahertz. And we operate this one time on an airborne sensor with an antenna which is 3 meters long. And we're looking at a distance of 3 kilometers. And I want you to calculate the range resolution and the azimuth resolution. And in the other case, I have a satellite, same frequency, same bandwidth, but I have a larger antenna and I have obviously a larger distance because the satellite is further away, okay? And you should know this, the velocity of light is the lambda, which is the wavelength multiplied by the frequency. And now you can try calculating these quantities over here. You have 10 seconds. And then I'm going to derive the solution. Actually, the solution is already more or less given on the slides. So the solutions are over here. The range resolution is 6 meters in both cases. And the azimuth resolution is 30 meters over here and 2 kilometers over here. Before we discuss these results, let me show you how we obtain them. The range resolution, this is the equation that I already showed you. It's the velocity of light, which is 2 times the bandwidth. The velocity of light, by the way, we know, it's 3 to the power of 8 meter per second times 2 times, and we have 25 megahertz over here. Now, when I want to know the range resolution, I don't solve this equation. What I do, I just remember one number. If I have a bandwidth of 1 gigahertz, then the range resolution is given by 15 centimeters. So there was a question in the tutorial before about the resolution or about the bandwidth given the resolution. I can calculate it here directly. I remember only this number. And now in the system that I have a bandwidth of 25 megahertz. So I'm going to go to 100 megahertz. I divide by 10, which means I multiply by 10, which means I have 1.5 meters. And then I'm going to divide by 4 again. So I have my 25 megahertz, which means I multiply by 4, which gives me 6 meters. And this is the result that we saw before. Concerning the azimuth resolution, again, this is what we have. This is my antenna beam width, which is the lambda divided by the antenna size. And if I want to know how much this is the beam width multiplied by the distance, and the distance is what we have over here. This is the R naught. And in the case that we had a frequency of 10 gigahertz, which means that the lambda is equal to 3 centimeters. And we had an antenna size of 3 meters. So now the azimuth resolution is given by 0.03 divided by 3 meters multiplied by the distance, which is 3 kilometers that we see over here. And now I'm going back. Oops. Here. Now we're going back to what we have. if we look at these results with a resolution of 6 meters laser, with a resolution of 6 meters, we are actually not too bad. It's still okay. With a resolution of 30 meters, we are not too good, but maybe we can live with this. However, if I work at a space agency and I go to the German government and propose to them a system which has a resolution of 2 kilometers, nobody going to give me the money to build the system. This does not work over here. Where's the problem? The problem is that we have a very large distance, so the beam broadens with distance, so we have a very bad resolution over here. And this does not work, and this now is the motivation to move to a synthetic aperture radar system, to the SAR system. And this was first patented by Carl Wiley in 1954 by a patent. And if you look at the patent, you see there's something mentioned like Doppler frequency, Doppler beam sharpening, and these things. And this is what I'm going to explain to you next, basically. So we have the same system as before. We have it on a satellite and we fly over a region, and now we want to get a good resolution of this region, both in range and in azimuth. The system that we are looking at is something like this. The principle of operation is the same that I explained before. Nothing changes. We are transmitting pulses. We are transmitted pulses, and in between we are waiting for the echo to be received. Okay, and this is the duration of the pulse, which is given by here, which should be long in order to have a good signal to noise ratio, and so on and so forth. And to explain the principle of synthetic aperture radar, I am going to use only one point on the ground. So I'm going to tell you, imagine that we have only one point, and I'm going to explain things based on this one point, and then later on, when you tell me, but I have a region, I want to generate an image, I'm going to tell you, yes, but we're talking about electromagnetic waves, and these are linear. So what is true for this one point is true for every other point in here. So it works basically in principle. So we are looking at a point, we're moving like this, and we're going to see this point. We're transmitting pulses, and we see this point during a distance which is determined by the beam width of our antenna that we have over here. And these are the basics that I'm going to use. Let's look at this basically from the side. We have the antenna over here. We are moving downwards. This is the beam width of our antenna, and this is the point that we are looking at. And I'm moving and I'm transmitting and receiving pulses, transmitting and receiving pulses. And when I'm here, I stopped seeing this point over here, or the antenna stops seeing the point over here. And what we have is, if I record all the echoes that I receive, all the signals during this distance over here, then this is equivalent to a very long antenna. And now a long antenna has a narrow beam width, which means it has a good azimuth resolution. This antenna is not real. It's a synthetic antenna, or an antenna which we synthesize out of the different positions that we have over here. And this is why we call it the synthetic length of the antenna. And this is also why we call it synthetic aperture radar, because we don't have it. Now, 2 comments about this. First of all, we are combining echoes at different positions, and this means that we need to be coherent in one way or the other. And second is, obviously we need a moving platform. If I don't move, I cannot build up my synthetic aperture. And these are the 2 conditions that we need to have. And now let's shortly derive the resolutions of the radar. We have a beam width of our element. So let me make a short drawing. I'm flying over here with a satellite or with an airplane. This is a point that I'm interested in. This is my beam width that I have, and the beam width of this antenna is given by lambda over d. Wavelength divided by the size of the antenna. Now, since I'm moving here at different positions, I start seeing my object, let's call it object, at this position. I stop seeing my object at this position over here, and I want to know this length over here. And the synthetic aperture length is obviously the beam width that we have multiplied by the distance, and the distance is this R naught over here. This is the R naught that we have. And if we insert one equation into the other, we have this one. Now, if I want to know the beam width of my synthetic aperture, I apply the same equation that I told you should know if you are electrical engineers. The beam width of the synthetic aperture is always the wavelength divided by the size, and the size is now the size of the synthetic aperture. I have to have a factor 2 over here, and the reason is that I'm transmitting waves and I'm receiving waves. So I have a two-way propagation here. And now if I put this equation into that equation, I have lambda over 2 lambda R naught over D. And what this gives me is D over 2 R naught. And now if I want to have the synthetic aperture resolution, then this is given by the half power beam width of the synthetic aperture multiplied by the R naught that I have. And if I put this equation over here, I get this result. Okay. I have a nice animation for this, which I'm going to show you over here. So this is the antenna. We are moving. We are collecting our pulses over here. The real size of the antenna is dA. We are not only transmitting 3 pulses, but hundreds of pulses, basically. And now we compute the synthetic aperture, and these are the equations that I just derived, basically. And this is the result that we get. And now I would assume that everybody should be angry at me and telling me this cannot be. This result, what you are showing us, is wrong. Because what I'm telling you is this azimuth resolution is independent of the distance. It's independent of the frequency and wavelength. And it's even counterintuitive, because if I make my antenna shorter, which means that the beam width gets wider, then the resolution gets better, because a small value over here is a good value. So the result over here is not what we would expect, although the result is true. And we need to explain this or to understand this from an information point of view. If I have a small antenna, then I have a large distance during which I see any point on the ground. And during this large distance, I'm collecting lots of information. And if I process this information in the correct way, then it means I can obtain a good resolution. And this is the idea behind it. And this is the main point that I want you to understand, today, basically. Just to mention something about this. This is an article also from one of the IEEE publications. It's about, they publish this once a year. It's winners and losers. It's basically the technologies that turned out to be working and those that turned out not to be working. And in this publication, you see already that other people, how can this be? The complication of the SAR data processing, it's very complicated, and you cannot really understand it. However, the basic principle behind it is simple, and this is what I just tried to explain to you shortly right now. Okay. A few words with this about airborne sensors. You already learned a lot about airborne sensors in the previous tutorial. So I'm going to go fast about this. This is a sensor of the DLR, which is maybe nothing special that we have. It works at different frequency bands. We have the resolutions and so on. How this works is that we have in the airplane different racks for the different frequency bands, and then you have this is in German, by the way, I just see. This is where you collect the data, you store the data, and typically in SAR, the data processing is done on the ground in most of the times. But nevertheless, you have a control computer where you control everything which is happening over here. Here you see a few images. These are the positions of the antennas over here. You don't see the antennas because you have a radome in front of them. Here, these are the racks on the airplane. This is the P-band antenna, which is looking downwards. And with this sensor, we are able to create nice images. You already saw this image over here, but I'm going to look at a different region, which is what you see over here. And I specifically like this image over here. You see the trees, which appear half like transparent, more or less, because they have volume scatterer. And these dots that you might be able to recognize over here, these are cows which are sitting on the field over here. And there's one cow which is sitting over here in the shadow of the tree. But remember, this is not the shadow of the sun. We have an active sensor. The active sensor provides its own illumination. We have our own illumination which means we are creating on our own shadow. So this cow is sitting in the radar shadow, and obviously it doesn't recognize anything of this shadow that we have over here. Okay, the different frequency bands were already mentioned in the tutorial before. I'm not going to elaborate on these. They basically determine how much penetration we have. I'm just going to show you an example, which is also taken by the airborne sensors at different frequencies. So this is at a frequency of approximately 5 gigahertz, whereas this approximately at a frequency of 400 megahertz. And I think this is in Indonesia, but I'm not sure. And if you look at the images, you see similarities. This is the rainforest area in both. You can see them. You see the dark river over here, and you see.
Sorry, but you have 2 more minutes.
I know. Yeah, I'm going to end after this example.
Okay, thank you.
Yeah. And you see this area over here, which is empty of trees. So you have a deforestation. And you see it here also, although it appears in the P-band image where you have a larger penetration, you see it larger. However, what you see here, you see these lines here and here and here and here. And these are actually roads which are below the trees. And which you don't see. We don't see if you look at the forest from the top, because they are hidden behind the trees. But if you have a penetration, you can see these roads over here. And I find this very interesting. It gives you one of the application, of course, of radar to determine illegal deforestation. And with this example, actually, I want to end the lecture today. Again, it was one point which I wanted to emphasize, and this is okay. I hope you understood this. And thank you very much, everybody.
Thank you very much, Dr. Marwan Younis, for the very thorough explanation about the fundamentals of the SAR, the synthetic aperture radar, and also some of the applications using the airborne synthetic aperture radar. We have 2 questions from the participants currently. So for the first one is, what is the difference between the SAR technology, the synthetic aperture radar, with the real aperture radar?
So with a real aperture radar, you have an antenna which you put at one point, and you have a resolution in range, which is given by your bandwidth, and you have a resolution azimuth, which is given by your beam width. And this azimuth resolution turned out not to be very good. Remember the 2 kilometers that we calculated in the example that I take you. In a synthetic aperture, we're using the movement of our platform to create a virtual, very large aperture, which gives us a very long antenna, a virtual long antenna, which gives us a narrow beam width, which gives us a very good azimuth resolution. So in one case, the azimuth resolution is not good. In the second case of the synthetic aperture radar, we have a very good azimuth resolution. I hope to have answered the question.
Okay, thank you. The second question is, why do SAR system have to be side looking? What will happen if the sensor will put on the nadir looking?
I actually, if I would have had more time, I would have explained this, because this is a very good question, actually. First of all, if we look down, remember, a radar measures distance. So if we have a point on one side or the other side of the nadir, then these 2 points have the same distance. So I cannot distinguish between them, because the radar measures only distance. So I have a left-right ambiguity, let's say. This is one reason, but maybe the most important reason is remember this range resolution, and the range resolution, if I'm looking like this, it's good. And the more I point downwards, the worse the range resolution becomes because of the geometry of the incidence angle. And if the incidence angle is 0, we divide by sine of the incidence angle, we have a resolution which is infinity, which means very, very bad. So if I look downwards, I have a very bad range resolution. And this is why we always look to the side.
Okay, thank you. We still have more time. If anybody have a question, you can type or just open your microphone to ask Dr. Marwan Younis. So we still have another 3 minutes, maybe. Actually, have a question about the fundamentals of SAR. What is the main difference between the airborne SAR and the spaceborne SAR? Do we have a difference in the acquisitions or the solution calculation?
It's actually not, because I'm just going to this equation. You see, this equation is independent of the distance. And this is interesting. Just to give an example, and we know that the AWACS airplanes, they have a SAR on them. And the AWACS airplanes, they fly very high. But the resolution doesn't depend on the distance. It's in the synthetic aperture, it's always constant. It does not depend how far away you are. And this also applies for the satellite. The satellite, the resolution is given by this equation over here. It depends on the size of the antenna of the satellite. So it's the same. This is also true for the range resolution. So there's no change in the resolution dependence on the distance. But obviously on a satellite, the distance is larger. So the attenuation, the propagation attenuation that you have is larger. So typically the signal to noise ratio of the signal that you receive is lower. So it degrades basically because you have a larger distance.
Okay. So I also read in the Sentinel-1, like they have the resolution of 10 to 10 meters, but actually the real resolution is about 20 meters or something. Is it true or?
And there's always a difference between the raw data resolution that you get and the resolution of the product that you download, basically. And the reason is that in all systems we do something which is called multi-looking, and it's a type of incoherent averaging that we do in order to reduce the speckle noise. So we do this averaging to reduce the noise, and this worsens the resolution. So we improve something and we pay for it by a worsened resolution. And this is why we have this confusion sometimes.
So the real resolution is the latter part, not the raw data resolution.
Yeah, and the raw data resolution is typically better than that of the product. And you can, if you know how long so the Sentinel antenna is approximately, I think, 12 meters. So the resolution, they could process a resolution of 6 meters, but what you get is worse than this.
Okay. We have 2 more questions. So very interesting, Professor, for the SAR explanation. What about the synthetic aperture sonar? Do you think that the SAR or SAS have this similarity? Do you have comments about that?
It's very interesting, actually, yes. In a very, very simplified way, we can say that with sonar, it's just the wavelength which changes, and the velocity of it's the velocity of the sonar, which we have in one case, and the velocity of light in the other case, and this is the difference. And actually, if you look at the old papers, the development of imaging systems, it was motivated by sonar systems. So these guys were actually first. They came first before they arrived at the electromagnetic waves. So there are similarities. Of course, the quantities, the physical quantities are different, but you can do the same with a sonar, obviously. And it's very interesting, and the people are good who do this.
Okay, thank you. Maybe this one is the last question for the Q&A session. Is it possible to detect a small object with a complete polarization, for example, of faces, or maybe people in the illegal logging, maybe detecting human during the illegal logging?
In forests now, you mean, or
Yes.
something like that?
Maybe just like a really small object within the density of forest.
The answer is it depends. It depends about the sensor that you're using, about the signal to noise ratio you have, which depends on the amount of transmitted power that you have. It depends whether you are using, which techniques you are using, whether you have a polarimetry or not polarimetry, and so on and so forth. But yes, there are examples for this. And if you look at for example, the publications of Kamal Sarabandi, they have done this, and we have done this also, that you look at small objects, you use tomography and these techniques to do this. So it's a small question, but a complicated question, because the answer is very long, and you need to explain lots of things of how to able to do this.
Okay. I think maybe the one that submit this question can search for the explanation regarding the tomography and else. Yeah. So I think this one is the last question, and at the end of this one is the end of the presentation. Thank you very much, Dr. Marwan Younis, for the explanation, and also thank you for all the presenters that are giving the presentation today. It was really a great presentation and valuable knowledge for all of us that attending this session. For the last session before we end this tutorial, I would like to remind those of you to check the important dates for submitting your abstract to the APSAR 2021, and reminder for the 5th tutorial that will be conducted on the 20th of May 2021. So before we end this, I would like to invite Professor Josaphat to give the closing statement.
Thank you very much to all of the teacher and also the participants who joined in 3 hours of the tutorial. Yes, especially I want to thanks to Dr. Agustan, and then Dr. Simone and Professor Marwan. Yes, and I think it's in Europe is still it's night. I'm sorry. Yeah, thank you very much.
Day. It's it's day for us.
Already. Oh, okay, good. Yeah. Actually, you know, the APSAR is our focus and main conference for the synthetic aperture radar in this Asia and Pacific region. And the symposium is always, you know, held in what is out of the year. Yes, and I hope you can join in our APSAR symposium in next November 1st to 5th. And actually this tutorial, this is one of our activity in IEEE GRSS, especially for the instrumentation and future technology that arranged by Dr. Marwan and Jose, and I'm also one of the co-leader for the UAV technology. And I hope all of participants also can join in our activity, you know, because we promoted some future technology, yes, and lead by the Dr. Marwan and Jose. And yes, fortunately from this week, I'm to be one of the co-editor of the IEEE GRSL, yes, the journal. And I hope we can promote, you know, excellent research and activity in our society. And I hope, especially for the Indonesian Remote Sensing Society, and also All Japan Remote Sensing Society, and can, you know, work together with us, yes, to promote a future technology, especially in synthetic aperture radar. I think we still have many, you know, chance, yes, to propose a new sensor, even it is the derivation from the synthetic aperture radar. Let's you know, working together, yes, especially in the corona, you know, situation. It is very hard for us, but let's do the best. And please keep healthy. And we still have several tutorial before the deadline of the paper. Yes, and please remember, yes, I want to remind you that the deadline of the abstract for the Aperture is next April 30. It is just remain 1 week. Yes, please help us to deliver this information to your college, your student, or your friends. Yes, I hope we can succeed. Yes, even we don't know about the situation in Asia Pacific, but for the corona, yes, but let's do the best, and I hope the vaccination activity in every country is work well, and then we can join in person at Bali. Yeah, Bali is, it is, I think, is a good place for us just to gather together. Yes. Okay, we wait at Bali. Yes. First is please submit your abstract. Yes, and we wait all of you. Yeah. Okay. Thank you very much, and keep healthy with your family. Yeah. Okay. Thank you, and I give to the moderator. Yes.
Thank you, Professor Josaphat. I think we have reached the end of the session. Thank you all for all of the speakers for joining us today and giving the talk, and also for the participant for joining us in the tutorial session. I thank you, and I urge you to stay healthy and keep following the health protocol during the pandemics. Thank you very much. Assalamualaikum
Thank you.
Thank you.
Thank you very
Bye.
much.
Thank you.